Okay, thank you everyone for being here. Today we have our speaker from actually Purdue, David Bernal. He's currently an assistant professor in the School of Chemical Engineering. Before joining Purdue, Dr. Bernal did his PhD at CMU in chemical engineering. His research is focused on optimization, nonlinear optimization in specific. And also before joining Purdue, he worked for 2 years as a research scientist in NASA AI lab for optimization.
Well, I'll tell you a little bit more about that.
Yeah, and I'll give you.
Well, thank you for the introduction. So let's get started. Yeah, my name is David Bernal, and I still need to figure out how to put the title of my things such that it's readable. But the picture that you see there is actually from the door of the chemical engineering department, and you're all more than invited to come visit us. Believe it or not, we're doing a bunch of optimization in that department as well. So a little bit about myself. Yeah, I think we covered this part. The reason I'm here is, besides the research, Professor Ana Maria and we overlapped at the Universidad de los Andes back in Bogota in Colombia, where both are from. After graduating there, I did an undergrad in chemical engineering, one in physics, a master's in chemistry, and then I did my PhD, as previously said, in Carnegie Mellon University. During that time, like through internships and through a couple of very lucky events, I was able to start working with the NASA Quantum Artificial Intelligence Lab, where we were exploring the use of quantum computing to solve problems in computational chemistry and combinatorial optimization, which is, that second topic is what we're going to cover today. Then I joined Purdue, and Purdue is a great place to be doing quantum because there is this Purdue Science and Engineering Institute. Purdue is the leader of the Center of Quantum Technologies, which is a big NSF center that agglomerates several universities here in the Midwest that do quantum information science and quantum computing related research. Maybe a small clarification, which allows me to tell you what I'm about to tell you, is the fact that I'm still associated with NASA and with an organization called the University Space Research Association. So while discussing what was going to be this seminar about, I had this rough choice of either choosing to show stuff that has been cleared by NASA or not showing it. I think that at the end, talking with Anna, we decided let's share something that has been cleared with NASA, such that it has like the cool graphics and the cool results and all this stuff, although it's a little teeny tiny bit outdated because I presented this at the SIAM optimization meeting in Seattle last July. Okay, so before we start, just a final note, my group is called Sequoia with a C because it stands for Systems Engineering via Classical and Quantum Optimization for Industrial Applications. So right now, this is our team. If you have never seen a Sequoia, it's absolutely fantastic. It's massive. These living things are beautiful, right? And that's my current group. And hopefully, one of our first activities that we did is that we planted 2 sequoias, 2 tiny sequoias. So hopefully by the time, I don't know, maybe I retire or my grandchildren retire, that's going to be a big enough tree such that you can fit inside of them. They are absolutely beautiful. Okay, cool. So I will unmute here, and yeah, that's pretty much it. And this is a common theme in my slides. I sometimes will pop out like those QR codes such that you can access the websites that I'm referring to. That, for example, points to my research group website. Okay, so certainly we have a lot of stuff to cover, so let me wrap up this slide deck, and thank you for your attendance. I'm kidding. I will show the second slide deck, which is going to be the ones that I will be talking about, which have like this funky design from NASA, which I love myself. And we're going to talk, although the title is different, it's pretty much the same content. So hybrid classical quantum algorithm for mixed interior optimization. So certainly, giving a seminar at Industrial Engineering where there is a strong operations research community, I wouldn't need to go too deep into this slide, but we're just motivating, like, why do we care about this mathematical, like optimization in general? So exploring the real world is costly, time-consuming, error-prone. So the way that we like to face the problems that we encounter out there is by distilling our knowledge of those systems in terms of mathematics. And those models, they need to represent the reality, but they have to strike like a very cute balance between tractability, how, I don't know, how would you be able to address those models computationally or analytically, and how accurate they are, the fidelity of those models. So certainly, like, there is this useful paradigm called mathematical programming where we write everything in terms of mathematical equations, and we like writing objectives and constraints, all with respect to certain variables. And here, these are the usual symbols that people use to show that. So by optimizing an objective, you can minimize or optimize it, and the constraints, they need to be satisfied. All of those are functions with respect to values that can change during your optimization search, which are called variables. Okay? I just wanted to set the stage, and obviously all of you are familiar with this. So unfortunately, the world that we live in is abrupt, unexpected, discontinuous, non-smooth, and here's where this thing of mixed integer programming plays a role. Because this, the fact that you can model some of those variables to be constrained to only take discrete values give you an amazing toolkit for modeling how the real world look like. And these conditions, they might arise from indivisibility. So if you're optimizing a production schedule and you're producing shoes, you wouldn't like to produce 3/4 of a shoe, right? But more importantly, they arise from triggers or switches in logical conditions. And that helps us model disjunctions, implications, precedents, and so forth. And using some words from Egon Balash, basically this is ubiquitous in the areas of decision making because you will encounter all these logical switches all around the world. Now, here comes my pitch. Besides discreteness, the world is nonlinear. So that, basically if you just assume, although it's enough to include discreteness in order to model the real world, you can summarize more information using nonlinear constraints and objectives, right? Because usually, like, if you go to other areas and you go to other departments, the equations that describe their understanding of nature, they happen to be nonlinear. That assumption that you can write objectives and constraints as a linear combination of the variables, it does not hold in general. And more importantly, this makes our problem really hard to solve. Okay? Cool. So this is how we jump into discrete nonlinear optimization. And for those in the audience familiar with this notation, we call it also mixed integer nonlinear programming. So this has to do with the fact that you have linear and nonlinear constraints and variables that can be either discrete or continuous. So, and this appears all over the place in chemical engineering. That's why they hired me. So process flow sheet optimization, process planning, molecular design, simultaneous design and control. But obviously, like, this is not only relevant for chemical engineering. That's why I'm giving a seminar outside of my own department, right? And there are applications all over the place. So I have a few here, some in medicine, some in civil engineering, operations research in general, computational biology, network design. Like, the applications of discrete nonlinear optimization are all over the place. In fact, you can always ask yourselves, like, okay, what kind of problem can I model using mixed integer nonlinear programming? And the short answer is every problem. The longer answer is that you can encode even Minsky recording machines, which are Turing machines. Hence, every computational problem can be encoded as a mixed integer nonlinear program. So at this point, if you have never seen this kind of optimization problems in your life, you're going to be like, oh, wait a second. This guy is coming over and telling me that every single computational problem can be modeled this way. Why am I not using this to solve whatever problem I often encounter? And the short answer is hardness. So these problems are complicated to solve, and if you're into computational complexity, they belong to the NP-hard family of problems. Even more, like you can even prove that simple, teeny tiny cases are undecidable. You cannot, like, it's not efficient to even prove that a solution exists. So, well, we are dealing right now with a complicated reality, which is we have a tool that helps us model anything that we want, yet solving it is complicated. So you can take two routes. You can be like, oh no, we cannot deal with these problems, so let's try to use other kinds of models and forget about this discrete optimization business because, I mean, who cares? It's going to be exponentially expensive. Or you can go the other way. Oh, yeah. So, and maybe just to support that argument, I could, like somebody like who is first introducing to this topic, they can be like, wait, even if there are a lot of solutions, you can just enumerate them. It's a finite amount. So just go evaluate all the discrete possible solutions and then check them for feasibility, filter them according to that, and then rank them according to the objective, right? That should solve your problem. And sure, it would, but it would take a lot of time. Not an infinite amount of time, but a really, really long time. So I love this plot because it shows on the x-axis the size of some problems that could be, for example, the simplest discrete optimization problem, which would grow as 2 to the n, and something like assignment problems, like traveling salesman problem, which grows as n factorial. And I also drew in the y-axis the number of possible solutions with 3 indicators of big numbers, right? The number of atoms in the universe, the age of the universe in nanoseconds, and so forth. So, I mean, it is completely impractical for us to even assume that we can enumerate the solutions in a discrete optimization problem. Yet, we want to solve them. So how do we do this? And maybe you have taken classes in integer programming, so this is going to be familiar to you. If not, allow me to introduce you to the ways that people use to solve these methods. So one of them is called this branch and bound method, and it has this computer science-y tree, which is the kind that grows downwards. And what you are solving on each one of the nodes of this tree is a problem where you ignore that some of the variables are discrete. If you ignore that fact, the problem can become easier because you are not dealing with this combinatorial complexity. Then after solving that problem, you adopt like a divide and conquer strategy where you take some of the variables that you know are discrete and then you fix them. You force them to be a discrete value around the solution of that problem that you ignored that they are discrete. You can keep doing that, and well, worst case scenario, you just have a tree of size 2 to the n because you end up branching all the way down. Obviously, this is not what we would like. We would go back to the plot in the previous slide. So what you do is that you enhance this with extra information from each one of the nodes to avoid that complete enumeration. And that information is encoded in terms of inequalities that you can add to your original problem. And since people like to understand this also geometrically, they can also see like cuts of some polytopes, right? So that's where this cut thing comes from. And in fact, like this has been super, super successful for linear discrete optimization. For mixed integer optimization, only in terms of algorithmic speedup, in the last 30 years, I mean, there are some papers that claim it's 150,000 times. So it's massive, right? On the other hand, when I see those results, I can, remember, I want to solve the nonlinear ones, so I can just piggyback on their success and be like, okay, let's try to solve mixed integer linear programs and somehow solve for the nonlinearity. So I can devise algorithms such that they break down my problem in pieces where each one of the pieces we count with an efficient solution method for it. And then through algorithmic tricks, I can just put together these solutions and convert, like, find the solution to my original problem. And if you're going to take anything out of the seminar, is that idea. That concept of decomposing the problem, breaking it down in tiny pieces that are more manageable, and then using the right tool for the right task. Okay? So, and certainly, like, this has worked. All right. So let me switch gears. keep that, like that main message. Can they sign already? No, not yet. Okay, anyway, regardless. So I'm going to switch gears, but eventually we'll go back to that main idea. And is there any physicist in this room? I'm a physicist. Anyone else? Okay, let's bring it. We're going to talk about physics for a little while. And I'm going to tell you the following experiment that Pierre Curie, who got a Nobel Prize in 1903, did, which I don't know if you knew about this, but basically if you have a magnet and you heat it up, it stops being a magnet. That is absolutely mind-blowing. Just think about it for a second, right? This physical system that has a very particular behavior, just by heating it up, it stops behaving that way. More importantly, like the point where that happens is very well defined, to the point that we call it like Curie temperature. And then you start wondering, like, wait a second, why is this happening? Why, like, the behavior of nature changes so drastically, goes through this phase transition? So let's have a mental model, all of us, which is the following. Let's assume our magnet is two-dimensional, and let's assume that a magnet is made of tiny mini magnets that are indivisible, okay? And magnets can only like be magnetized north or south. Let's assume, for example, that south is green, north is red. So in this figure, do we all agree that there is more green than red? So this, according to that mental model, that would be a magnet, okay? Suddenly what happens is that when you start increasing the temperature, some of those greens flip to red. And we end up in a situation where there are as many greens as reds. So they basically cancel each other out, and we can agree that that figure on the right is not a magnet. So this mental model, exactly that mental model, was proposed by Lentz in the 1920s. And what you can do is, okay, these pieces, they can interact with their closest neighbors. And the way that nature is described is by minimizing the energy. So you can write down this equation over here, right? This optimization problem. You minimize over +1, -1s, reds and greens, of the energy that they share with their neighbors, plus their interaction with the environment. And he gave that to his PhD student. He gave a simplified case where you remove this term, you only consider the one-dimensional case, and his PhD student solved that problem analytically. For that, the model, we know it nowadays as the last name of the PhD student, not the professor. So this is the Ising model, not the Lentz model. Okay, took 25 more years for Onsager to solve analytically the two-dimensional case. He got a Nobel Prize for that and some other things. And it took then 60 more years to prove that you couldn't solve analytically any case that had more dimensions or more complicating factors, just by a proof with combinatorial optimization. So I'm sorry that there are no physicists in the audience, because this is absolutely brilliant, right? From the physics perspective, like this notion of universality where phase transitions happens in systems that have the same symmetries and dimensions that earned Wilson a Nobel Prize in 82. And this model, this Ising model, is the simplest one in theory space that is able to show this phase transition. Hence, it's like our first step towards explaining how systems such as water or magnets behave. It's absolutely amazing. Now, for this audience, though, it is interesting because this problem is equivalent to a subcase of those discrete optimization problems that I was telling you about, those nonlinear discrete optimization. In particular, it is equivalent to something called a quadratic unconstrained binary optimization. No constraints, all the nonlinearity is quadratic, subject like contain the objective, and the variables are 0, 1. Okay? So then we can talk again, like I guess I can skip this slide, because this slide is a dictionary. If you have, do you know any physicists? Like, do you happen to interact with physicists? They are real people, like we talk to them and they're friendly and everything. But often we need these kind of slides in order to establish a conversation with them, because they have different terms for different things, even if it's the same model. So this builds up like those relationships, right? So they call it energy function or Hamiltonian, we call it objective function. They call it spin variables, we call them binary variables, and so forth, okay? And they do like really fun stuff with this model because it's a normalization probability, and they talk about partition functions, and you name it. One particular thing that we, because I just happen to be both an optimizer and a physicist, so my two personalities collide on are solving the model. So I told you in the previous slides that these physicists had solved the model analytically. But in that case, why is that relevant for us optimizers, right? If the problem is already solved, who cares? And here comes a big semantic difference between these two communities. Solving, in that case, is identifying like this expected value of the variables. For optimizers, we do care if each one of those mini magnets is red or green, because sometimes, like what we're going to do is we're going to map our problem such that that corresponds to 0, 1 variables. And you need to know in the solution of your optimization problem whether that's a 0 or a 1, because that means, for example, that the truck is covering this path or this other path. So you see how this is not quite the same? And certainly, like some of us care about global optimality. Sometimes a good one suffices. Okay, so this Ising model. How do you solve it? With an Ising solver. Thank you for attending my talk. This was a great pleasure. No, never mind. Okay, what's an Ising solver? The Ising solver is something that hopefully we'll try to get into this in this cartoon to go to those wells. And what's interesting is that because this problem is so ubiquitous, both in physics, and we'll show how they appear also in optimization, people have started building algorithms and hardware that can solve this problem more efficiently. So you can pass that model to Gurobi, if you know what Gurobi is. But there are also like all these classical thermal annealing things and other classical algorithms. Some people call them quantum inspired because they take some inspiration from quantum mechanics to do that. Other people just go the hardware way, and so our colleagues in electrical engineering, they start building literally circuits that try to solve this problem. So we have oscillator-based computing, coherent Ising machines, and quantum approaches. So maybe you have heard about quantum annealing or hybrid quantum classical algorithms. So that's where we're going to dig a little bit deeper. Usually I get this question every time I start talking to somebody about what I do, because I'm in the quantum computing group at NASA, right? So they're like, why does NASA care about this, right? Why is this relevant for the bigger field of quantum computing? And in fact, well, the conversation on why NASA cares about quantum computing is a longer one to have. But why is this Ising kind of research related to the quantum group at NASA? Basically, because we love these problems. We like benchmarking, studying them, and using those solvers. We have developed some classical codes that implement that. We collaborate with some folks building computers with light, which we call coherent Ising machines. We, and I say we, when you heard about this quantum supremacy experiment by Google, people, what they should say is that there was a quantum supremacy experiment by Google, Oak Ridge, and NASA, right? So part of the co-authors of that paper were at this team, and we actually had one of those devices at home, well, at home at the office, right? So we were able to play with them. And hence, and more importantly, we are waiting for something called fault-tolerant quantum computers to come along, because there is like a bunch of algorithms that we can apply to solve these Ising problems, these QUBO problems. Okay? Cool. So, but how? I will go, I will resolve that. No, let's resolve it right away. So quantum states are super fragile in the sense that whenever they interact with the universe, something happens which is called a measurement, and for all practical purposes, their quantum state is destroyed, and you go back to a classical state. A quantum computer, you would like to keep it on a quantum state because that's where you can take advantage of this weird phenomena that happens out there. Now, as you can imagine, keeping that quantum state for a long time is complicated. It's an engineering challenge. So what although so spoiler alert, there are quantum computers out there, and you can use them and you can interact with them. They are very limited in the sense of what kinds of algorithms they can run, because they are prone to error. You cannot shield that chip good enough for it to not interact with anything in the universe. So there are proposals where with bigger, better computers, you can avoid these errors by using something called error correcting codes. Once we get there, once we get a computer that is big and good enough, they will not be prone to these faults, so they are going to be fault-tolerant quantum computers. We're not there yet. We're not even close, to be honest. But you can predict how these computers are going to behave. Quantum mechanics, like the equations are well understood. Hence, many people, they have spent their time designing, assuming, okay, if you give me a quantum algorithm, I should be able to implement this, this, and this, and this algorithm. And then you can prove stuff. You can actually like predict, once these devices are built, which we don't have yet, there are some algorithms that are going to behave this way and this other way. So let me put more details into this. So we had agreed that our optimization problems, or at least the ones that I'm showing, cannot be solved efficiently because they belong to this NP-hard complexity class. And even though you can do these proofs with the algorithms that are to be executed on quantum computers, and for some problems, you can actually prove that there is going to be an exponential speedup with respect to the best known classical algorithms. There is, and here, like we get into hand-wavy zone, there is not much hope that this can be extrapolated to optimization. And the reason has to do with these complexity classes. Basically, and this is, again, assuming that P is not equal to NP. So there is a complexity class called BQP where you can prove if a problem is out here, it would take a non-polynomial, non-deterministic polynomial time to solve on a classical computer, but it will take a polynomial time on a quantum computer. So you would have exponential speedup. What people are pretty sure about is that NP does not belong to BQP. So that means all of the optimization problems that I care about, they live here. They live outside of the boundary of those problems that can be solved in polynomial time using quantum computers. So there is not much hope. Like if you were wishing for me to come here and tell you, oh yeah, we're going to get exponential speedup for discrete optimization, I'm sorry. But this is not the message that I want to bring to this audience, okay? Obviously, like if P equals NP, this whole thing collapses, and at that point, why do you even need a quantum computer? The word would be very different, by the way, but whatever. Nobody has been able to prove it. If you happen to, there is $1 million waiting for you out there, okay? So anyway, but my view on this is that, and going back to the beginning of this talk, geez, already half an hour? We deal with exponentially hard problems on a regular basis, right? If you attend classes on integer programming, this is your bread and butter. That does not stop us from trying to solve them really hard, right? And so although we can prove that you would get some asymptotic speedup, that speedup is not going to be exponential, it's still quite interesting. If you go back to industry and you tell them, look, remember that optimization problem that took 10 weeks? Now I can solve it in 1. Even if it's a polynomial speedup, well, they will pay millions for that, right? So that's the sort of approach that we should take here. It's hard to predict when are we going to get that scale up. There are no quantum advantage for practical optimization problems yet observed. And, but these heuristic speedups are of interest. Okay, cool. So I took this from a paper that I wrote where obviously I consider the most general optimization problem that you can face out there to be the one that I described in this very same seminar, these discrete nonlinear optimization problems. And I use this map to show you more or less the state of the art in quantum algorithms for optimization. So this area that includes SDP, semi-definite programming, and linear programming, there are algorithms, such as the ones that I was describing to you, where people have done the math. And they tell you, if you give me a fault-tolerant quantum computer, I will be able, for example, to do pivoting on simplex exponentially faster. There is this other, obviously, that is subject to those devices being built. This other area, the blue one, is where we were starting our conversation, which is discrete, unconstrained, binary optimization, not discrete, but actually quadratic. And because of its similarities with the physical problem that I described earlier, like many people are working on that area because there are heuristic and approximation methods designed for that kind of problems, which happen to be discrete optimization problems and of interest of a community, that includes me. Okay, so that was a lot of introduction. So let's jump into the matter. I give you a quantum computer, a current quantum computer. How do you solve a discrete optimization problem? So some history, Einstein said stuff about some adiabatic hypothesis, but basically you can design something called a quantum adiabatic algorithm, and it works in the following way. You have a system, and the system is sitting at a given state, and that state has a well-specified energy. Then I start transforming the system, not the state, the system. And if I do that slowly enough on an adiabatic way at 0 Kelvin and so forth, even if I end up in another system, which most likely is going to have a different state because of the way that this energy works, what I can guarantee is that the energy ranking is going to be the same. So if I started in this system at the lowest energy state, at the optimal solution, and I transform that into another problem, I can make sure that I will be at the optimal solution of that final problem. And there are convergence proofs, and this is super interesting and a complete different way on the way that we tackle optimization, because suddenly, instead of changing the solution, changing just the values of the variables, what we're changing is the problem. I find it absolutely fascinating. I don't know you. I mean, at this point, I was like, oh my God. Okay, anyway, so this is a nice cartoon. You're starting the green landscape, and the red ball is at the bottom of it. And if you transform grid into purple, where purple is arguably more complicated, the red ball is going to be at the lowest stage of that purple landscape. That's more or less what I just said. So this is the quantum adiabatic algorithm, and it was proposed for discrete optimization because you need these energies to be discrete because of the magnets and all this stuff. And although this is an idealized algorithm because you need to, like, on theory, you would need to execute this at 0 Kelvin and an adiabatic condition and so forth, which is unphysical, you can try really hard to get as close as possible to those conditions. So that's where this quantum annealing comes by. And it's just the practical implementation. So they tell you, oh, you cannot be at 0 Kelvin. Let me try really hard to keep this chip at 15 millikelvin. That's colder than outer space. This thing, it's just a shield. This black box here is just a shield from pretty much anything. That in there is no air. They're like electromagnetic waves. They just bounce. Even the foundations of the building are cut around that box such that it doesn't vibrate in case of an earthquake. But you want to isolate that system in order to be able, hopefully, to go back to this idealized algorithm. That's how these quantum devices work, okay? And then there are a bunch of non-quantum things that try to simulate this behavior. Now, the other quantum computers that we have access to, and I needed to include this here, are quantum computers where we give instructions in terms of gates. Maybe if you are a little bit curious about this topic, you have heard about Qiskit and how they do all these tutorials, and you access IBM devices and Google devices and so forth. And there, the approach is very different because you give a bunch of instructions. You give digital instructions. The previous case was just analog computing. You have like this smooth transformation between a state A and state B. In the other case, like with your computers that you have right now, you're giving digital, like discrete instructions. Does that stop us to do optimization? No, not really, right? So if you had access to one of those computers, the proposal is the following. You map an optimization problem that you care about to a QUBO or an ISINC. Second step, you assign each one of the qubits, which are these indivisible states of quantum computers, which can be 0 or 1 after performing a measurement. They correspond to your tiny little magnets. They correspond to red or green. The third step is that you apply a circuit, which is a series of instructions inside of that quantum computer, such that the probability of sampling the optimal solution is maximized. Easy peasy. The fourth step is that you get some solution after performing these transformations, these digital transformations on them, and you perform a measurement. And because of the rules of quantum mechanics, there is a probability like this. They might be inherently, like the measurement is inherently probabilistic. Hence, you might get, even if you run the problem exactly as you designed it, you might get the wrong solution. But these things are so efficient that you can just afford to run it 10,000 times, 1,000,000 times, and then you get a distribution. So certainly people with your skill set are already more than qualified to understand this, because you work a lot with probability distributions, you work a lot with optimization. These are basically, you work with like you design software and so forth. This is already the skill set that is required to do these kind of things. Now, obviously, at this point, if you're paying attention and not asleep, you're going to say, wait, number 3, what do you mean apply a circuit? What the hell is that, right? Like, do you apply a set of, you apply a set of digital operations aiming to maximize the probability of measuring something you don't know what it is, because you don't know the solution of your optimization problem. If you knew it, you go back home, and then you don't use the quantum computer. Well, here comes like some fun thing, which is, remember that algorithm that I told you about moving smoothly between two states? You can, like, there are proposals on discretizing this algorithm. Like, it's a very like bird's eye overview of the algorithm, but it's just discretizing and trying to follow that continuous path. So this is how this algorithm is called QAOA. It has been renamed a couple times. The original name was Quantum Approximate Optimization Algorithm. And if something comes up to your attention, is the fact that it has approximate in its name, meaning that it's an approximation algorithm. If you're familiar with approximation algorithms, it's a super rich area of optimization, which is, you have a hard problem. We all agree that it's complicated solving these problems efficiently. Okay. So scratch solving the problem to global optimality. Let's come up with algorithms that run fast, polynomially in terms of the size of the problem, and whose solution is guaranteed to be within certain threshold of the true optimal solution of the problem. That would be interesting, right? Because if you say, look, your problem is super complicated, it will take me the age of the universe to give you the solution. But I could give you this super efficient algorithm, and it would give you a solution that would be, what? Within 10%, within 5% of the true optimal solution. Would you take it? I would, right? So these, and here, again, the skill set of industrial engineering and operations research come out because the people that know about approximation algorithms usually sit in departments like this. And they were able to prove approximation bounds by putting together these two things. So beautiful, right? So we talked about quantum annealers that try to implement this physically and gate-based computers that try to implement this digitally. How am I doing on time? Jeez. Okay, yeah, I haven't even started showing about the research, but I thought, you know, like, come on, let's show them an intro. Who has been to a quantum computing lecture before? There you go. So sorry about that. Yeah, I bet you know all of this. It is what it is. So anyway, we have these two alternatives that make use of quantum behavior to solve discrete optimization problems. So yeah, let's talk a little bit about them. So the first one we talked like is the physical implementation, and there is this Canadian company that makes these devices called D-Wave. Maybe you have heard about it out there because you can play with those devices and you name it. For gate-based computers, like again, like are this discretization-like approaches. The most known is QA08. There are something called variational quantum algorithms or eigensolvers, which people like in chemistry because they look a lot like some stuff that they use to compute the minimum and like the stable configuration of molecules. And if you were to solve a discrete optimization problem using IBM or Google quantum computers, you would need to go this route. Okay? Nice. So maybe the next question that might arise is, okay, how good are they? Like, is this really worth it? On the quantum annealing side, there is this figure from a group at Los Alamos, friends of ours, who posed a problem, an optimization problem, and discrete, quadratic, unconstrained. And they gave it to a bunch of competing alternatives, including Gurobi, which are Gurobi is the blue line up there, right? And a bunch of other heuristics, the other lines. And the black line over there is the quantum annealer. What is this? X-axis, execution time. Y-axis, solution, like objective function value. And actually, relative difference, so the gap, what people call it. If you solve a problem to 0.5% gap, you would be happy. The quantum annealer took what? 20 seconds. All the competing alternatives to get to that level took around 100 to 1,000 seconds. And more importantly, and this is beautiful, is that the white dots that you see there, they also account for the time that it takes because you're not going to have the quantum computer sitting on your room. So you need to send the problems over the internet, and then they get downloaded, processed, and sent back to you. The white dots account for that. It's still faster than all the other alternatives. So it's already showing performance advantages. Obviously, like classical optimizers would jump at you and would say, oh, no, that's limited by size, by connectivity, blah, blah, blah. It's a heuristic. Sure. 2 seconds, 1,000 seconds. Pretty compelling argument to me. Second part of it, the approximation algorithms, the stuff that runs on the gate-based computers. When it was first proposed, obviously doing this kind of analysis is really tough. It's really challenging. But so you need to simplify the problems, or at least better characterize the problems that you can give approximation bounds to. They took one problem out there, which is called E3 lin 2. And why is this relevant? Because when that algorithm came out, they were able to prove the best approximation ratio out of any algorithm out there. So it, like the stuff that runs on gate-based computers was proved to give better approximation ratios than any competing classical algorithm. Now, there is like a continuation to this story. The classical optimizers look at that paper, got inspired, and they're like, oh, wow, these ideas are really cool. They applied it back to the classical algorithms, and they were able to beat that approximation ratio. So if anything, so parenthesis here, this is already like, some people claim like, why do you want quantum computers? They haven't allegedly solved any practical problem yet. And to that argument, you can respond, even without building a single qubit, the studying quantum computing is already giving us advantages. At the very least, it's inspiring classical optimization. At the very least, it's inspiring non-quantum researchers to do stuff from a different angle. And it already paid off. This is one example. I'll show you later a couple more. Anyway, So these are even more limited by size and noise, yet they are interesting. So time to start the actual research. So let's go fast through this. I worked on benchmarking of classical algorithms, and this is something that we wanted as a team to bring into the field of quantum computing. And then when you start comparing things across different devices, technologies, accounting for the fact that they output not a single solution but a distribution, you need to start like redefining what a success metric is supposed to be. And here we have something called time to solution, which, I mean, we can go through the derivation, but it's basically like the time that it would take for you to have a 99% certainty that you have a solution within a threshold. People use this all over the place. It became like the academic standard, and then you have like all these comparisons of all those competing technologies. So you have like the quantum annealers versus the classical methods versus Gurobi, and that's the way how people like doing this. I only introducing this because I will be talking about time to solution, but it has time units. It basically says the solution time. Okay, so one last thing that I wanted to bring up to your attention is, okay, where do these Ising problems come from? Let's go back to optimization. So cool story, bro. Nice that you talked about quantum computing. How do I use this for my applications, right? I am in an industrial engineering problem. I want to tackle some industrial problems with this. And first of all, there is this famous paper that took all the NP-complete problems. If you're into complexity theory, you might recognize Karp's 21 NP-complete problems, and they mapped them into Ising and Q. Like there is a mapping. Now, these mappings are inefficient. You can do some reformulations. Go back to discrete nonlinear optimization, and using this Qt recipe, you can turn that into a cubo. If you have continuous variables, you discretize them. If you have integer variables, you binarize them. You encode them as binary vectors. If you have nonlinear equations, you quadratize them. And you have constraints, you penalize them. Besides the first one, the other three are exact reformulation methods. The first one is an approximation. And it's so simple to describe that we just went ahead and implemented a whole software suite on Julia for you guys to use it. So basically, let's assume that, oops, sorry, I'm going a little bit ahead of myself. Let's assume that you already have your problems modeled in Julia using the Julia mathematical programming language. You call our package, hey, can you give me a cubo out of this? And we will get this done well for you. Since you never had to encounter the case where you had to do each one of these by hand for every problem that you tried to, this is a blessing. This is absolutely blissful. And we also connected already with D-Wave, with the IBM software package to use their devices. MQLib is some initiative created by the people at MIT to benchmark this kind of stuff. So, and we're planning to get some extensions. Okay, anyway, the point is, this is so simple it could be automatized. And each one of these points, they lead to some weaknesses in the reformulation. If you are discretizing continuous variables, well, you're increasing the size of the problem because you need to get a lot, like how much resolution do you want on your continuous variables? Integer variables into binaries, they usually lead to extra variables or horrible coefficients. Nonlinear equations into quadratics, there is this pseudo-Boolean optimization theory, which introduces a bunch of extra equations into the mix. And constraint penalization, if you have ever done like Lagrangian optimization or something, you know how tricky it is to find those multipliers. And softening those constraints can have like a big cost. So regardless, like it's automatic, you just use the code, you just use the software. And then we take a time machine and we go back to the middle of the talk where I said, this is the only thing that I want you to remember of this seminar. What was it? What was it? Nobody? Jeez, I failed.
Instead of solving for the variable, we can get to solving, reformulate it into a new problem and solve a new problem.
Fair enough, it goes along those lines. It's on decomposition algorithms. You're going to take your problem, and instead of just trying to force feed it into a solution method, maybe break it down in pieces, and maybe those pieces you're going to have like efficient tools to solve them with. And this is the pitch of the talk. We want to use decomposition algorithms. I don't claim I'm the only one thinking about this. There is a bunch of other people out there coming out with proposals. And if I had time, I would show you all of them. But apparently I don't. So the Julia code, just scan the code and you'll be able to use it. We did a bunch of work with some folks from the Federal University of Rio and a company called PSR. A lot of work in software engineering. We are covering more constraints than everyone out there. We are covering more solvers than anyone out there, and we're fastest than every single alternative reformulator out there. Whatever, right? Decomposition algorithm. So we went together with some folks at Stanford, and we were like, oh, we were still like classical optimizers before this whole quantum thing started. And we were like, if you really wanted to solve these constraints, you really wanted to enforce the constraints and you don't want to penalize them, can you do something clever about this? And we ended up ending in something called copositive optimization, which if you know something about conic programming, is a really challenging kind of conic program. But going that route and motivated by the constraints that quantum computing was giving us, we came up with an algorithm which, long story short, is beating Gurobi. Gurobi is the leading commercial tool that solves these kind of problems. And whenever I say that, you should be like, oh, wow. Okay, all right? So we get a solution that beats Gurobi. There you go. Yeah, thank you for playing along. Okay. So how much time do I have? 2 minutes. I don't think we have enough time to cover what we did. So I will tell you why did we do it and how did it result. And then we can talk about details later. We wanted to solve a problem of this kind, which is objective, which is quadratic, possibly non-convex, linear equality constraints, non-negativity constraints, and some of those variables are binaries. And this appears in neural network verification, model predictive control, many NP-hard problems, scheduling, routing, you name it. So we're using some conic reformulations to come up with but this is like the reformulation was not new. We did a little bit of theory, just proving like some strong duality here and there to make sure that if we solve the dual of something, we'll get the actual solution. But the point is, like, we ended up with that problem, which looks kind of easy, right? It's a linear objective subject to a matrix belonging to a convex set. Now, this problem, you can go back to complexity theory, and it's co-NP hard, like co-NP complete. Like checking if something is inside of outside or outside of this cone is complicated. But, and here comes the interesting part, the fact that it's convex motivated us to come up with an algorithm. And for the integer programmers in the audience, cutting plane algorithms should be something that you would be very familiar with. We came up with a cutting plane algorithm where the red part of that algorithm requires solving that problem over there, right? Which is quadratic, continuous, unconstrained, which looks a lot like the problems that we solve with these cubosolvers. So we showed that the other part was polynomially expensive, you name it. And then we were trying to check how good our problem was. So we had some test cases doing max clique. And here some results. So first, we implemented everything classically with our new algorithm. Everything running Gurobi and all this stuff. And you notice green are all the operations. Like, remember the boxes that I had? 2 green boxes and 1 red box, same colors here. The red one is the one that takes the most time. The time axis is logarithmic. So what we propose is take that red time and reduce it using the right tool, maybe some quantum-inspired methods. That's exactly what we did. So that's more or less how it works. We communicate back to the Ising solver, and the Ising solver spits something that we turn into cuts. So eventually, we implemented this We didn't even have to run a quantum computer for this. We literally went and took an open source implementation of simulated annealing. And suddenly, if you start comparing the time that it takes to solve a problem, x-axis time, y-axis objective, the lines that merge, that's Gurobi. The vertical lines, that's the simulated annealing method, just for the verification step. And it happens across all the sizes. We get speed ups of 1, 2, 3 orders of magnitude. So when we put this together with the whole thing, it only works on sparse graphs. Answer no, it works with dense graphs as well. This was the compositivity check when we implement the whole algorithm and compare it to our two-cubo reformulation and all this stuff, we end up with these plots, which in summary is the green line. Green is us, blue is a heuristic method, and the other lines are Gurobi. No, the red one is Gurobi. What do we get from this? So you would be like, they look kind of similar, to be honest. And yeah, you're right. They look kind of similar, but you're forgetting the fact that the axes are in logarithmic scale. So we're talking like differences there. They account for a lot. The other thing, more or less what we can argue, is we have the same scaling as a heuristic. We have the same scaling as the classical heuristic. Hopefully, if we use a quantum computer for this, we'll get the same scaling as the quantum computer. And we get the same convergence to global optimality as Gurobi. And we are already able to beat it in the larger cases. So, and we love open source software, so we put it out there just for you guys to use it, try it on your own problem. We want to do some generalizations. I'm terribly over time, so conclusions. If this is the first conclusion, like this discrete nonlinear optimization is a really powerful and versatile modeling tool. If you have never used it, I do highly encourage you to visit it. Those problems are also hard to solve. Hence, we need to do a little bit. It's not only about calling like commercial tools and getting a solution out of them. Sometimes it requires us to sit down, to take a step back and design algorithms. And through those advanced algorithms, what we would like is, for example, to take advantage of physics-driven, physics-inspired methods, quantum computing, coherentizing machines, and just adding them to our toolkit such that we're able to solve these problems with novel hardware. And obviously, the work is at the algorithmic level to take advantage of the modern hardware. The moment that fault-tolerant quantum computers come by, well, what about if we're ready and we already have algorithms ready to take them? So, oh yeah, finally, obviously, like these are older slides, but the internship program is still running. So there is an internship program called the Feynman Quantum Academy, where we hire undergrad, graduate students to do research in the Quantum Artificial Intelligence Lab at NASA. Since my commitment to NASA has decreased, I'm only right now advising a single intern, whereas I had several back in the day. But it just happens to be that one of the members of that team is at Purdue. So reach out. We're always looking for good people, and if you want to work on this, why not? Okay? Thank you for your attention. I'm sorry.
Thank you, David. Do you have any questions for the speaker? Everyone is busy scanning.
No. There is a question back there.
Thank you for the talk. In the second body of work that you showed, have you found any trends where you'd be able to suggest to someone based on the farmers tools they have for you? It's better to use rural units for your it would be better to use the
Yeah. So that's a great question, and basically identifying where would you use this, like our method is not a silver bullet. It's not going to be best in every single case. And if you paid attention to those plots, the red line was better in most of the plot, right? In fact, like for tiny problems, just setting up the whole machinery in our algorithm was too expensive. Now, when the problem is big enough and complicated enough for Gurobi to choke, that's where we are showing better performance. Predicting where that is going to appear, That's a harder one because it's dependent on the problem itself, it's dependent on the sparsity and something like that. Just a note on that, if you guys like machine learning, there is this very beautiful research project which is giving all these problems, given all these solvers, you solve them, all the problems with all the solvers, and then you train a classification method for a practitioner that comes out with a new problem for you to tell them, oh, use Gurobi, or oh, use David's algorithm, or use this other thing. That's a really cool project, something that I really want to work on. So if that is interesting to you, please reach out. Thank you for the question.
Any more questions? Okay, let's then thank the speaker again.
Thank you. Stop sharing here. I'm sorry, I went over time. I talk too much. I don't know if you noticed. Where should I leave this?
You can leave it on the desk.
Hi, how are you?
In the room, just wait to scan the barcode.
You sent me an email.
Oh, right. Yes, I
about the
did.
flyer.
So, what is this? Is it on a,
It's a seminar that's.
but it's on a brewery?
Yes.
That is so fun. It was unclear from your message, but I would very gladly like.
So please scan the barcode. It will take you to a Google form, fill it in. That would be how we would be counting the attendance. What the one that you signed by hand is just a back. Okay?
I myself would go.
And where are the attendance sheets?
Is actually having a plan. It was from different performers.
Okay.
And
Oh, fantastic. Well, this is great. I mean, this obviously is one of the seminars that I teach, but I teach, not yet at Purdue, but I teach at Carnegie Mellon, a class on quantum integral programming. So can you connect the two of us? It will be super interesting of you. Yeah. My student, maybe you met him, Albert Lee. Maybe. I don't know how many people attend that, but I told him